This is a microcomputer that works without a microprocessor. Instead, it has a discrete processor made of 74 series logic ICs. These also generate video and sound without the need for any dedicated hardware. Therefore, the system can be connected to a VGA monitor where it supports a resolution of 160 by 120 pixels and 64 colors. Furthermore, it features a 4-channel 4-bit audio synthesizer and is controlled by an NES-compatible game controller. Thus, the Gigatron functions as a fully blown 80s microcomputer that can be used to play video games. Its parts are still easy to get and the schematics and software are on GitHub. So you can build one yourself, either on breadboard or on PCB, as you prefer. There's also a kit available, but instead of messing with all 38 chips, I opted to implement it on the Tang Nano 9K, a low-cost FPGA board. And this is how the Gigatron works. Its 8-bit arithmetic and logic unit is made of 2 4-bit adders and 8 multiplexers. With this it can do 8 arithmetic and logic functions. Its results go into 8 parallel D flip-flops, the accumulator. There are also the X and Y registers which hold the memory addresses. The X register is made of 2 4-bit counters and contains the lower 8 bits of the 16-bit address. The Y register addresses the upper 8 bits. The output register is used for video signal generation. Each 2 of its outputs connects to 2 resistors, forming 3 simple 2-bit DACs, 1 for each color. This setup provides 4 levels per color, which results in a total of 64 colors. At last, the remaining 2 pins output the horizontal and vertical sync signals. The upper 4 bits of the extended output register connect to an R2R ladder, a simple DAC for the audio. The lower 4 bits control the 4 so-called blinken lights LEDs that always blink like so, but are otherwise useless. Game controller inputs are processed by a shift register that acts as the input register. The operating system and programs are stored in an EEPROM with 16 output bits. With this, the opcodes are 16-bit wide, where the upper 8 bits form the instruction and the lower 8 bits the operand. The system also includes 32 kilobytes of static RAM. All these core components are managed by the control unit, where instructions are decoded by hardwired lookup tables. Their outputs control all the previously mentioned components. The Gigatron uses a Harvard architecture, which means that programs and data occupy separate address spaces. This is different from most modern computers, which use a von Neumann architecture where code and data share the same memory space. A processor with Harvard architecture works very efficiently. It can execute an instruction and can transfer data within the same clock cycle. So video generation is straightforward. There is an instruction that reads a pixel value from RAM, writes it immediately to the output register, and increments the X register which holds the lower memory address. Then the next pixel in memory can be immediately written out in the following clock cycle. The command is repeated 160 times until the end of the line is reached. Although a VGA frame typically comprises 480 lines, the Gigatron's vertical resolution is only 120 lines. To fit the 120 lines into a 480 line frame, each line needs to be repeated 4 times. Besides generating the video signal, a computer must also execute programs, process user inputs, and manage sound and other things. The Gigatron cleverly uses the time during the blanking intervals around the sync pulses to perform these tasks. To run its programs even faster, the Gigatron repeats each line only 3 instead of 4 times, and so gets an additional time slot to run applications during the omitted line. This does also enhance the retro feel of the display and makes it look a bit like a legacy CRT TV. Users can adjust the number of repetitions by pressing the select button on the controller and so choose to display each line once, twice, 3 times, or 4 times. It is evident that the programs run faster when fewer lines are displayed. To not mess up the video timings, applications run in a virtual CPU, or vCPU for short. The vCPU only runs during the blanking intervals and the hidden lines, and emulates a 16-bit processor. It has its own 16-bit instruction set that's completely different from the native 8-bit instructions used by the TTL core. Most programs, however, are written in Gigatron Control Language or GCL, a language developed exclusively for the Gigatron. It looks a bit cryptic because it's very machine-oriented. But if you want to program the Gigatron without learning that weird language, there is also a C compiler for the vCPU. And to complete the 80s look and feel, there is a port of Tiny Basic, so it can also run basic programs. An FPGA is essentially made up of lookup tables and flip-flops that can be configured to perform any logic function. These are then connected together like it's done in actual circuits. So, FPGAs can be seen as tiny little breadboards made of silicon. I've made a video explaining how FPGAs work and how to use them. Feel free to check it out if you're interested in diving deeper. FPGAs are programmed using hardware description languages like Verilog. In a Verilog project, each file defines a specific module, like the Gigatron's control unit here. While the schematic might appear confusing at first, modeling these components in Verilog is straightforward. It's all done with a few lines of code that reminds of a C program. I have ported the Gigatron onto a Tang Nano FPGA board. Its HDMI connector allows it to connect directly to a TV or monitor via HDMI. However, the original TTL Gigatron does not feature HDMI. But Goin, the manufacturer of the FPGA, supplies a ready-to-use Verilog module for this purpose. Simply connecting a USB power supply to one side and a monitor to the other brings up the Gigatron's main menu. Naturally, you might also want to connect a game controller or keyboard, or even a VGA monitor. However, these devices typically operate at 5V TTL levels, whereas the Tang Nano can only handle 3.3 or 1.8 volts at its I/O pins. To bridge this gap, we use level converters. These are available as modules that can be easily put on a breadboard. After I found that everything worked perfectly well, I decided to build it in a more stable and reliable way. So I designed a PCB in KiCad, and with the new PCBWay plugin, I sent it directly to the website. Just click this button here and immediately the website pops up, displaying previews of both the front and rear sides, along with the dimensions. There are tons of options to customize the PCB to your needs, but in the vast majority of cases you can leave them at the defaults. If you don't like the usual green solder mask, there are alternative colors available. I chose a red solder mask with white silkscreen. And PCBWay not only makes PCBs, they also offer CNC machining, sheet metal fabrication, 3D printing and injection molding. Also check out their module store where I got my Tang Nano board from.
A few days later,
the boards arrived. They look and feel great like always, and I'm looking forward to assembling them. Let's fire up the soldering iron now. Unfortunately, the level converters are only available in SMT packages, but luckily there's a version in a relatively hand solder friendly SOIC package. We need at least one of these. The other two are necessary only if you plan to use VGA or want to develop additional extensions. It's good practice to use blocking capacitors of 100 nanofarads between VCC and ground, although the circuit also works well without them. If you encounter no problems and prefer not to fiddle with these, you can omit them. And here's the finished Gigatron board. At last, I plug in the Arduino Nano into the pin headers. And there we go. Let's get everything hooked up and try. Unfortunately though, its HDMI socket is only wired for video and therefore not usable for audio. And VGA is also not capable of audio, so there's an RCA jack for that. And here goes the game controller. The TTL Gigatron features an EEPROM with 64K 16-bit words that stores the system and apps. In contrast, the FPGA has only 38K words of integrated flash that take the role of the ROM there. This means that it can hold fewer applications. Although the Tang Nano has an onboard flash with 4 MB, we cannot use this instead. That's because it is connected via SPI, which is a bottleneck that makes it too slow for our needs. So I had to reduce the number of apps from 12 to 8 to fit the ROM file into the 38K flash memory available. Applications are hard-coded into the ROM, and the ROM files are built using the GNU Make tool. This means that adding or removing programs is a tedious process. First, we need to change the list of included applications in the Make file. and in the menu as well. The main menu itself is a program written in GCL, and all changes must be made in its source file. When finished, type make in the terminal and wait a minute or so for the flash to be written on disk.
Please hold the line. Bitte warten Sie. Restez en ligne, s'il vous plaît.
The flash file is a plain ASCII file filled with 32-bit hex values and their addresses. This must then be flashed into the internal EEPROM of the FPGA through the GoWin programmer. However, if you just want to try out a program, there's a simpler way. Here I have an Arduino Nano with a sketch amusingly named Babelfish connected to the controller port. I now start a terminal emulation and open the virtual COM port of the Arduino. There I hit C to turn on echo mode to see what I type, and then R. The Babelfish then navigates to the loader app and starts it like a game controller would do. Then I type P0 for Tiny Basic, which is then sent from the Babelfish to the Gigatron's RAM over the game port. The command T switches the Babelfish to terminal mode, which allows us to type directly on the Gigatron. However, this solution still doesn't satisfy me entirely, as the programs need to be statically linked into the Arduino sketch. The programs available are stored in the Arduino's program memory, typically as ordinary C header files filled with hex values that make up the actual vCPU code. Using the Python script sendfile.py instead is the alternative. It accepts two parameters, the serial port number and the path to a program file. There are many of these in the apps folder, so let's pick Tetronis, a Tetris clone for the Gigatron. More programs can be found under Contrib. There you can find what different people have contributed to the Gigatron project. And I put all schematics and code you need to build the Gigatron on FPGA there. Now the right moment has come to help the algorithm and hit the like button. And don't forget to subscribe and enable notifications to never miss anything. Big thanks to all my patrons for their great support. As a patron you get previews without ads and all that begging for subs. Your name will also be shown in the credits at the end of the video. The sendfile script can also run basic programs. Let's throw a file from the basic folder on it. Now Tiny Basic is launched first, and then the basic program is automatically typed in and started. And that's it for now. Thank you for watching, and thank you to all my patrons on Patreon.